This is Metabolic Mastery, a core medical technologies podcast dedicated to advancing knowledge and practice in metabolic testing. Welcome to Metabolic Mastery, brought to you by Core Medical Technologies. I'm Dr. Marc Humbert, and this is my co-host, Dr. Cameron Garber. And today we're going to be talking about metabolism.
But we're getting nitty gritty here. We're going back to our roots.
So one of the questions that we get is, how does the CardioCoach actually turn breath data into how many calories are burned, what fuels we're using? How does it know that from just what we're breathing?
Yeah, I was at a conference the other day and somebody kind of called me out on it, and I was like, so he was like, well, how do you know that this information is valid? And I was like, oh, we've had validation studies and things like that. And he's like, no. How do you know that the science behind it is valid? It's like, well, they're kind of known constant values and stuff. And he's like, well, tell me about it. And I was like, how nerdy do you want me to get? Like, how do we need to go back to the Krebs cycle and like electron transport chain? Like it just caught me so off guard because I hadn't had to get quite that in the weeds with it. But people do ask all the time, how does this work? How does it take breath data, like you said, and turn that into calories burned and all the other metrics that we can measure? And so I was like, yeah, we probably should talk about that. Like, how does this work fundamentally? Some people out there may have a foundation in this and may understand that, but it's always a good refresher. In preparing for this episode, it's always fun to kind of go back through it. And, I was watching last night while I'm on a lawn tractor, watching or listening to a YouTube video on the Krebs cycle again. And, just like refreshing, like how many ATP are created. And this video was like, it's actually a range and not an exact value and different studies. And I'm like, oh, yeah, interesting. Okay. It's just funny to refresh it and go back over it again, just so I have it straight in my mind. And yeah, it's good foundational principles to know.
Yeah. And what we're going to attempt to do with this episode is try to put it in fairly plain language. You'll have to forgive me. I may struggle with that.
Yeah.
but like with this, we may not, we may gloss over certain things,
right,
just in an effort to not make this a textbook.
Right. This isn't quite 30,000 foot view. This is a little more zoomed in than that, but we're not going to go like, this is your biochem lab level detail. So we kind of, as we were prepping for this, we're talking about like, we need to do it in fifth grader language so that it's, detailed enough that people understand it, but simple enough that they can then explain it to somebody else. And that's the key, is that you can explain the basics of it to your clients so that when they ask you questions, you're not going, kind of like I was at that conference to a scientist researcher. That was the audience. And I was like, calling me out. It was funny. It was good. It actually was really good. And he apologized later. He's like, sorry, I just kind of like to do that to people and put them on the spot. And I was like, it actually was good. It was good. So anyway, funny.
Absolutely. So the basic idea is that we can't, without being very invasive,
right,
we can't see directly what's happening inside the cells. But what the breath data tells us is basically the footprint of what's happened in your cells. And so, we call the process of breaking down food into energy cellular respiration, right?
Mm-hmm.
Your cells are kind of breathing, if you will. And so because we know that's happening at the cell and certain byproducts are released from that cellular respiration and those make their way into the breath, then that allows us to factor in some of those things. And so let's talk about what metabolism actually is first off. And that's something that, often people are like, oh, metabolism, like that has to do with like how heavy I am, right? Or that has to do with fat loss, right?
Yeah.
And metabolism is actually so much broader than that. It's literally all of the building up and all of the breaking down processes that are occurring across time throughout our body. And so it's the summation of those building up and those breaking down processes occurring.
Well, so with all of these breaking down and building up processes too, a lot of that is breaking down our food and then using that to build up our body. And so in breaking down our food, some of what we get is building blocks for nutrition and being able to have the basic building blocks we need to build up our body. And then the other part is creating the energy that we need to fuel our activities. And so that's such an important part of the whole thing is essentially we take food plus then oxygen that we use to help break apart that food once that food gets into our cell. So we're not going to go through the how our food gets from our gut tube to the cells. That's a whole nother piece of biochemistry.
It just does.
Yeah, it magically gets broken down and transported to our cells in the form of like fats and carbs predominantly, or what we talk about. Typically, if you're burning a high amount of protein as a fuel source, something's wrong. It can be used as a fuel source, and it is used as a fuel source, but it's not a primary fuel source. Typically, proteins are used for those building block purposes more than energy.
Yeah, and so when we're using indirect calorimetry, which is what the CardioCoach uses, it's assuming a non-protein contribution.
Right.
Just because under most circumstances, the addition from protein is fairly fairly
Negligible.
negligible.
Yeah.
Could not say that word.
Some mornings it's just tough. Yeah, and so that's the idea. We're looking at the fat and carbohydrate utilization as oxygen helps to oxidize um, those fat and carbohydrate molecules. It's essentially breaking apart those things into carbon chains that then can be broken apart, you know. And so oxygen is part of that chemical process that helps cleave those carbon chains off. And in breaking all of that apart, we have byproducts then. So it's kind of food plus oxygen, and then we get all of these different byproducts that come out of that. And so those different byproducts are then used by our muscles and other cells as a form of energy.
Absolutely. So we're going to talk a little bit more about that utilization of carbohydrates and fats in just a second, but I want to talk briefly about our body's energy systems, right?
Hmm.
How are we actually creating energy? We've talked about this before, but we have three primary energy systems. The first one is our ATP-PCr system. So we have some amount of stored ATP in our cells. It's a pretty heavy molecule, if you will, and so we don't store a lot of it. We also have the phosphocreatine stores. So when your trainer's telling you to take extra creatine, what that's doing is saturating the muscle cells with creatine that can be used for quick energy. And so that is a pretty small source of energy, but it still participates. The next is our glycolytic energy system, and that is what happens in glycolysis. So that takes carbohydrate, breaks it down in the cell's cytoplasm, and then that creates a certain amount of energy, right? A certain amount of ATP. ATP again is the body's energy currency, if you will. And then the third system is our oxidative system. So that's the one that is using oxygen to create energy. And so all of those three systems, sometimes people are like, oh, it's this one and then this one. All of those energy systems are basically always working together. It's kind of like a dimmer switch on any given system, depending on the intensity. And so the quicker we need energy will depend on the system being used. So the nice thing about the oxidative system is it can produce a ton of energy. Fats are very energy dense. And so a lot of that oxidative process comes from fats, but we also use what's left over from glycolysis in part of that oxidative pathway. But just the underlying idea is that it can create a lot of energy, but it's not as quick as some of those other processes. And so if intensity increases, then we're going to need to use more of that glycolytic system. And then eventually very high intensity, we're going to have to use that stored ATP, that phosphocreatine, because we need energy so quickly. And that's basically just the quickest way to get it to us. Anyway, so that is, in a nutshell, is our three energy systems. Any nuance we missed there?
I don't think so. I think you nailed it.
Okay.
So with the again, it's with those energy systems then. So we're using those to fuel different phases of exercise.
Mhm.
So fats are obviously used at lower intensity, longer duration activities. Carbohydrates are used all the time. So we're never not burning some amount of carb, or very rarely, I guess. Um, so it helps keep the fire going. Carbohydrates do, but it's also what's used when we're doing higher intensity stuff, because it burns hot. And then essentially, and then those like phosphocreatine or the first few seconds, those quick energy systems or those first few seconds of quick burst energy or when we first start doing something.
Yeah.
So those different phases, I think that's important to understand with that.
Yeah. And so, we'll get to how those show up in the breath data,
Yep.
depending on the fuel being used.
Yep.
So first is carbohydrates. So again, a quick, easy fuel. So that carbohydrate in the cell, the first process is again that glycolysis, that glycolytic process, right? What's fueling that glycolytic energy system? And so the carbohydrate is taken and it's cleaved apart, and we get pyruvate from that. Pyruvate has two pathways. It can either be shuttled into the mitochondria and be processed there, which we'll talk about in a second, or it can be converted to lactate, and that lactate can be shuttled out of the cell and be used elsewhere. So lactate can be used by nearby oxidative muscle fibers, by the heart, lungs, brain, kidneys, etc. I will. I promise, Cameron, I will not soapbox about the lactate.
You did. As we were talking about it, I was like, "Can we do this episode without going on a soapbox about lactate?" And he's like, "I'll try."
So that was my brief. Lactate is created. It can be shoveled out and used elsewhere. So
I love it.
That's my miniature soapbox.
And it is not lactic acid.
It's not lactic acid. Just to be clear. Thank you, everyone listening. Okay, so we've cleaved that carbohydrate apart in the cell and created pyruvate. That then goes into the mitochondria where the Krebs cycle occurs. And so Cameron's now going to
well, I think one of the things to understand with this, I'm going to let Marc do the explanation of the Krebs cycle because remembering the exact numbers and stuff like that, that's his game. But I think why this matters is to understand more about, as you're doing exercise, to understand how much is going on behind the scenes and why it's so important to create those pathways. There's a lot more going on than just burning carbs or burning fats. That those pathways require certain amounts of sustained fueling. And so the more blood vessels, the more pathways we have for delivering that from fat stores to the muscle, from our lung, oxygen from our lungs to the muscle, the more capillaries, the more all of those things we have help to fuel that and make that more sustainable. Whereas when we are unfit, we have fewer pathways there to deliver those substrates to the cells. And so then it becomes a much more difficult process to do the work and go through all those chemical processes as quickly. And so that's some of the limiting factors when we're not fit, is just being able to get the nutrients in as well as clear the byproducts away. So we're creating byproducts of, carbon dioxide, of water, of H plus ions. So we're making an acidic environment, all of these things, and we need to get rid of that and clean that up. And so sometimes our limiting factor is getting rid of stuff. Sometimes our limiting factor is delivering oxygen and calories to the cells. But that's one of those big limiting factors. And so I think as I think about the Krebs cycle and, all of these things, I think part of why that's so important is that these processes take time and are quite complex. And so the more resources we have for dealing with it, the faster we can do that, the more we can keep up with it in our exercise.
Yeah.
And that's why training is so important, is it creates those chemical signaling pathways that help build up those systems so that they are more efficient and things like that.
No, that's such a great point because we can break down at any point along the line, right?
Right.
We're getting oxygen in, or transporting it, and then we're utilizing it at the cell. And those other two, right? Those last two, the oxygen transport and utilization in the cell are often the biggest bottlenecks.
Yeah.
And so building those blood vessel highways,
Yeah,
essentially.
that's exactly
And I think you pointed out something important too of it's not just the delivery to the cell, but it's also taking those metabolic byproducts out
right.
and dealing with those.
Well, and that's a lot of people that really is more of the problem and why they feel like in their muscles and things like that, feel the fatigue, whereas a fit person doesn't feel the muscular fatigue quite as much. And it is more of that buildup and byproduct and stuff like that. It's not lactic acid burning the muscle. Um, but it's just that we're kind of choking it off by not clearing out the old stuff. It can't get enough of the new stuff in. And so that's where we feel those, energy requirements not being met and the bog down and all of those things.
Yeah. Well, and having more and better working mitochondria help us to deal with a lot of those metabolic byproducts. So basically, what's happening is when the cell gets overloaded with metabolic byproducts, the environment gets too acidic, and the cell's like, I got to get this out of here. So it shuttles it in the blood. We have really great systems for buffering those byproducts.
Mhm.
And so that's part of what creates some of the CO2 that we breathe out
Yeah,
is buffering those metabolic byproducts,
right.
which is great, right? So we increase our amount of respiration, uh, simply our breathing frequency, right? Breaths per
Yeah,
minute, and that helps get more of that carbon dioxide out. But if we have a lot of mitochondria and we have very efficient mitochondria, then they can process those better. And so what happens is when we are um, going through that glycolytic process in the cell, we create some molecules that can be used inside the mitochondria.
right.
And so
You
what
you're you're talking NADH and
Yep. Yep.
FADH? Yes. Yeah,
Exactly. And so those H plus ions that are generated
yeah,
within the cell, those can actually be attached to um, NA, NADH and taken to the mitochondria where those can be um, basically shuttled into the mitochondria through a variety of processes, which we're not going to get into the
right.
detail of that.
Well, yeah, so it's that the Krebs cycle that Mark was
Yeah.
asking about, also known as the citric acid cycle.
Yeah.
So it's a fairly complex chemical process where essentially you've got these chemicals, NADH and FADH, that are combining with adenosine diphosphate and having another phosphate put on there so that it can be ATP, which is the energy currency, like Mark said. And so that's kind of the simple is you're taking some of these breakdowns and combining them back together basically to be able to. So it's this cycle that goes through and you wind up spinning off a bunch of ATP molecules that we use for energy. So that's what our actual muscle uses. It doesn't use the carbohydrate per se. It uses ATP that we break down from in this citric acid or Krebs cycle. They call it the spinning wheel because some of these molecules keep re-entering the cycle to be able to get the balance of hydrogens correct, basically. And so it keeps re-entering the cycle to get that balance of hydrogens correct to be able to put that extra phosphate onto the diphosphates. So now you have a triphosphate, and that's that adenosine triphosphate, the ATP. And so that's what's happening basically is this series of chemical processes that create ATP. Now you have this big bunch of ATP from it only takes a few ATP to create quite a few ATP. And now all of a sudden we have all this energy that our muscles can then use. And so the way muscles work, it's kind of cool. The way that ATP binds onto a certain part of the muscle that makes it changes the chemical structure of the proteins for a second and allows these little pieces to like grab onto one another and pull down as that chemical structure changes shape, which I think is so fascinating.
Oh yeah.
How cool is that? And that's what creates a muscle contraction is essentially chemical reactions happening that change the structure, the shape of a protein temporarily. And so, I mean, how cool.
Oh, it's just so cool, all the
Yeah.
different, reactions and mechanisms that are working at any given time in our body. Like, it really is this finely orchestrated process,
Yeah.
and it's like, when you get down to the nitty gritty, it's like, wow, like we're doing all of that in a given time. Like it's so cool that we're
Oh,
able to live lives as long as we are, right? With like,
without even thinking about,
yeah,
I didn't think about, I better get that ATP to cling on to that muscle fiber,
yeah, yeah.
and yeah. Anyway,
So basically, we have that quick energy being created in the cell via glycolysis, and then some of the byproducts that are created from glycolysis are basically used as a sponge to soak up electrons. They're transferred into the mitochondria,
yep.
and then in the mitochondria, that Krebs cycle. So that helps to regenerate some of those chemical sponges so that they can go back into glycolysis and continue to bring more electrons back into that process. Krebs cycle will also spin off some carbon dioxide, which has to get transferred out of the cell. We ultimately breathe that out. We'll get back to that in just a second. And then electron transport chain, right? We just mentioned that we're using those electrons to feed that chain. What's happening in the electron transport chain is we're using it to um, to generate the ATP. So we get hydrogen ions that are, correct me if I'm wrong on this, we get hydrogen ions that are pumped out of the intermitochondrial membrane into the intermembrane space. And then as those flow back in, that spins a little wheel called ATP synthase, and that creates energy. We actually, this is just a little side note, some of our energy or some of our heat energy is actually produced in that process as protons leak out without spinning that that ATP element. There's little proteins in the membrane that allow some of that to leak out, and it produces heat.
Yeah,
Anyway,
yeah. Well, so that's what allows things to pass through the membrane of our mitochondria. So our mitochondria almost has like its own wall within the cell and the cell wall. So the wall of that mitochondria has little channels that allow those ions to pass through so that they can get through more quickly. And sometimes things leak out the channel the wrong way.
absolutely. Yep. Yep. So anyway, we have that process that creates ATP, and then oxygen is that final electron acceptor in that process. So it accepts those electrons. It also combines with some of the H plus, and that creates water. And then we get rid of that through breathing some of it out through sweat, urine, and other bodily processes.
Yeah. Yeah.
And so I think the yield with carbohydrate molecule after going through that whole process is about like 34 to 38 ATP, depending.
So, yeah,
Yeah,
that was
there's a
really
range.
interesting. They debated that for a while on the video that I watched
Yeah.
last night, and I was like, I knew there was a range, but from 30, they claimed some studies were as low as 30 and as many as 42.
42.
And I think some of that depends on conditions, and that's what they said. The important thing to remember is that it's a range. It may depend on conditions, on all kinds of things.
Well, also on
Needs
fuel use, am I breaking down glucose or am I breaking down glycogen? That's
right.
going to depend.
Right. Yeah. Fuel type, and then demand and need. So is there enough substrate to be able to make that chemical reaction more efficient or less efficient?
Yeah.
Like, is there too much byproduct buildup? That I think that's probably what slows it down, is if you have too much byproduct buildup, then you're probably not getting as many ATP per whatever. That's what I was thinking during it anyway.
But I think the big thing to understand is that it's outmatched by how much ATP we can create from a complete breakdown of a fat molecule. So fat molecule, I think, is around 108 ATP or something like that.
Yeah.
It's just significantly bigger than what we get from a molecule of glucose or glycogen.
Right.
And so that's kind of the big thing to understand, is that fats are just so much more energy dense,
Right.
which is great, right? There's a reason that we store them, because they're incredibly they hold so much energy within them.
Well, yeah. So in previous episodes, we've talked about the analogy of like the furnace and burning oak logs versus paper and like a pine log, and that carbohydrates are more like the pine log, the big heavy hardwood oak logs, and then the phosphocreatine is like what? Matches, paper, or yeah, something
Dryer
that's
lint.
drier lint. Yes. Oh, the cotton, from cotton trees,
Oh, yeah.
cottonwood trees. We had a neighbor that burned the local church's shed down. It bordered on his property, and he had gathered up all the cotton from his cotton trees and lit a match, and it just went boom, like so aggressive, and it caught the roof of the the shed on fire and burnt the shed to the ground.
Oh man, no, that cottonwood gets everywhere, and like,
It's the
yeah,
worst.
it's the
Anyway,
worst.
but that's a great example of like that quick acting energy where it just goes so fast that you can't keep up with it, but it's gone in an instant.
Yeah,
Creates a ton of heat and energy, but gone really quick.
yeah,
That's the phosphocreatine stuff. Whereas, yeah, you've got more like pine logs and whatever
yeah.
and the hardwood. Okay.
So why do we go into that nuance? Because the amount of each substrate, right? So fuel, fat versus carbohydrates that we're breaking down is revealed in the breath. And so, as Cameron mentioned before, we need a certain amount of oxygen to metabolize those molecules, and then a certain amount of CO2 is produced. And so that is reflected in what we call the RER, or the respiratory exchange ratio. It is your volume of CO2 divided by your volume of O2.
Or known as the respiratory quotient.
Quotient. Yeah.
Everything has two names for some reason.
Yeah. So respiratory quotient is typically used when they're referring to the actual muscle cell, and then respiratory exchange ratio is as reflected in the breath. But for our intents and purposes, those can be pretty much equivalent. I know people listening, there is a difference,
Right.
but just when you see that, it's referring to essentially the same thing.
Right. Sometimes they're used fairly interchangeably, and I don't know, it's semantics somewhat, but there is a difference for
Yeah.
sure. Yeah.
So let's talk about, we'll briefly go over the breakdown of carbohydrate. We won't get too much into it. But if we're breaking down a molecule of glucose, that's C6H12O6. Did I get that right?
I believe
Okay.
so.
So
Well
anyway,
done.
thank you. So to fully metabolize that, we need 6 oxygens, and then we get 6 carbon dioxides. So when you divide the carbon dioxide, 6, by the oxygen, 6, you get 1. And so we would get a respiratory exchange ratio of 1. And so that's telling us that it's on the carbohydrate side of metabolism, right? We're burning mainly carbohydrate. For fats, the typical molecule that we use for that reference is palmitic acid. I'm gonna have to look at that one. I wrote it down because I don't use
I
it
was
as
gonna
often.
say, if you
Yeah.
pull this one out, I'll be impressed.
So C16H32O2.
Okay.
So there we go. So to break that apart completely, we need 23 oxygens, and then 16 carbon dioxides are produced. And so 16 divided by 23 gives us 0.7. And so that would be the respiratory exchange ratio of 0.7. And so that's going to be more exclusively fat burning. And so depending on where we are from 0.7 to 1.0 is going to give us an idea of, am I burning more fats or am I burning more carbohydrates? And often it's more of a mixed fuel use. And so depending on the exercise intensity, we will likely use more fat, and then as that intensity increases, we'll burn more and more carbohydrate to fuel that. To fuel that intensity.
Yeah, I just as a general rule, most of us throughout the day, just cruising along, probably hover between, depending on how fuel efficient we are and things like that. But most people hover kind of between 0.8 and 0.9 through most of their day. And so beyond that is either, yeah, higher levels of exercise or not very good fuel efficiency if we're above zero point 0.9, or below 0.8 means you're pretty fuel efficient, or you need to eat something.
Yeah.
So
So
yeah, that but that zero point 0.8 to 0.9 is like 60% fat at 0.8. We're ballpark around 60% fat, or 2/3 fat, 1/3 carb, and the zero point 0.9 is about 1/3 carb, or 2/3 carb, 1/3 fat, if that makes sense, on the zero point 0.9 range.
yeah. Well, and so there's some cases where we can see lower than 0.7. So if people are in true ketosis,
Right.
that's a different equation. And so that'll draw, so like sometimes like 0.67, 0.68, things like that. We actually tested someone that was like in a truly ketogenic diet, and they
So they
actually
were
had
in
that
a true ketotic state.
state.
And then, yeah. And so yeah, it was really hard actually to get them to actually a 1.0 or higher on their exercise test, because they were burning ketones,
Yeah.
which was really interesting.
And then,
Fascinating to see.
it was absolutely, yeah, it's always interesting to see
Elite
the,
athlete that lives a ketogenic
yeah, well,
lifestyle.
what's the thing, like qualified for,
Oh, he's won like a bunch of 250 and 300-mile races
yeah,
and all kinds of stuff. Yeah, he's amazing. Oh, you're talking
yeah.
Marty.
Mhm.
Oh, she was the one that qualified. So we've tested a few. We were thinking of different
Yeah,
people,
I know
but
you're talking
both
about
of them
though.
were
Yeah.
similar. Yeah, she qualified for the Boston Marathon and the Ironman World Championships in the same month that she qualified for Medicare. It was really fun. But yeah, she considers herself low carb. She still does eat carbs. She'll fuel with carbs for events, but most of her training and most of her lifestyle is very low carb.
Yeah.
Yeah.
And then when we go above 1.0, we're essentially getting extra CO2 from buffering that as a byproduct in the blood. So that'll end up getting a little higher
Yeah.
than 1.0. Okay. So now let's dive into, okay, you've gone through like what's happening in the body, how, oxygen you used, carbon dioxide you used. How do we know some of the other things? Like, how do we know how many calories you're burning based on what you're breathing in and breathing out? And I think that's a common question we get. Like, how is
Oh,
this
big time.
box that's just taking in my breath? Like, how does it have any idea about what I'm burning?
Yeah.
And so we're going to take a brief history lesson.
Oh, I love it. The history of indirect and direct
Direct calorimetry.
calorimetry. Here we
So
go.
when we say direct calorimetry, um, it's basically the how is food converted into energy. And so the original thing they did was what was called a bomb calorimeter. So they basically took food and they burned it, and then like so in burning that food, how much did it raise the temperature of a given quantity of water?
Right. So the definition of a calorie is the amount of energy required to raise 1 cubic centimeter of water by 1 degree Celsius. Right?
Yeah. Or if we're
I
talking
think I'm
about
I think I'm defining that.
so when we're talking about calories,
We're
we're typically
talking
talking
kilocalories.
kilocalories.
Yes.
And so that is the amount of heat energy to raise 1 kilogram of water 1 degree Celsius,
Okay.
which is
One
probably the
kilogram.
same.
Yeah, yeah.
I'm sure like the
The conversions
volume
are the same. Yeah,
conversions.
yeah.
Yeah. Yeah. Anyway,
Yeah. What? Yeah.
and so anyway, then what we did is to test humans, we built big rooms, right? So a direct calorimetry room, and it's a completely sealed room that has water pipes running through it. And as the water is coming into that room, it's the temperature is measured. So we know the temperature, and then from the heat the body gives off while they're doing whatever in that room, just sitting there or often exercising, how much heat is given off, and then that goes into the pipes and changes the temperature. And so that temperature difference lets us know how much heat was put off. So now we have indirect calorimetry, which is what the CardioCoach uses, the type of technology. And so how do we get from the heat someone gave off to oxygen? Well, what they did is they basically built a room that did dual things. So it still had those water pipes running through it, and so it could measure the amount of heat given off. But then also the person's gases were collected. So how much oxygen they're breathing in, how much carbon dioxide they're breathing out, and those were measured and compared. And so what they found was that for a given liter of oxygen, about 5 calories were produced, and that's big C or kilocalories.
Right.
So for every liter of oxygen that was consumed, the person gave off about 5 calories worth of heat.
Right. So it ranges from like 4.95 to 5.05 ish.
Yeah,
I believe,
depending.
if I'm remembering that correctly. It's
Yep.
been a minute.
And so because that relationship was established, we know now that when a given amount of oxygen is consumed, that's going to take about X number of calories to burn it.
Yep.
And so as Cameron mentioned in the beginning, right? It's like lots of foundational science was done on this. These are established constants, yes, that are known. I could not think of that word.
Yeah.
And so we can use that to calculate the amount of calories used. So the commonly used equation in indirect calorimetry is the Weir equation. So it's basically just taking the oxygen consumed, carbon dioxide produced, and converting that to calories using that established relationship of 1 liter of oxygen to about 5 calories of heat. And so anyway, now because when we put the mask on, right, that's collecting all of their breath data, it's feeding into the machine, and then we can use that to calculate calories. And because we're getting both oxygen and carbon dioxide, we can calculate that ratio, VCO2 over VO2, or the RER, to get an idea, again, as we talked about, of the amount of calories that we're using. Okay, so um, so now let's talk about, in a simple way, like, how the cardio coach, like what's actually happening
Yes.
from the person to the cardio coach.
Right. So that's really an interesting thing. There are certain sensors within here. And so Mark and I have said several times on the show, like, what's being measured is actually fairly simple. So oftentimes when people are like, oh, the device must be not working right, a lot of the time it really isn't the device, because foundationally it's only measuring a few key metrics. So it's measuring humidity and barometric pressure and some of those other things, just to take those things into account and whatever. But actually during the test, the main things that it's measuring are flow. So right inside here, so in both of these, the exercise and resting test ports, there is a flow sensor. And so what makes Core's flow sensor unique is that it doesn't have a turbine. It doesn't have moving parts. And so it stays calibrated for decades, for years and years and years. They're amazing. And that's kind of the claim to fame with Core. And so you've got the flow sensor that, as the air first enters, it measures the flow of the air, how much air is being moved. And then inside, there's a mixing chamber where it gathers all of the expired air, mixes that together to homogenize the sample, to make it all a representative sample of what we blew out. And then it goes past an O2 sensor and a CO2 sensor. And so at its basics, like, that's a fairly simple system with three main sensors. There's other things, other sensors and stuff, but those are the three main sensors that we're using. And we get so much data from that. When we combine that with heart rate, our flow, our oxygen, and our carbon dioxide combined with heart rate, we get so much information about how your body is functioning and physiologically how you're doing. We learn about your muscles, about your nervous system, about your lungs, about your cardiovascular system. Really, just about every body system we get some insight into. And when we have comorbidities, we often can look back at your test and be able to identify how that's affecting you. So now we can't always say, oh, because of this on your test, you must have this problem, or we can estimate your brain health or your lung health or things like that. Doesn't work kind of in reverse. But if we know you have a lung function problem, we can often pick that up on the device. Or if you have a brain function problem, we can often pick that up on the device. We can't use the information to say, oh, you must have a brain function problem. It can allow us to ask questions that lead us down that path. But pretty simple device when we really break it down into what's the main things that it's measuring. And so it does that. I'll let you describe the oxygen and carbon dioxide fuel cells and how that measures that.
Yeah, so it's actually really cool.
Yeah.
So the oxygen it uses a galvanic cell,
Yeah, the galvanic fuel cell.
fuel cell,
Mhm.
and so as the oxygen hits that, the cell reacts a certain way, and then that lets us know the concentration of oxygen, and then that's fed into the system, and then that oxygen concentration is mixed with the flow data to give us what's the volume of CO2 or of O2 that's being utilized. Oh,
Well, so but part of that, the galvanic fuel cell, part of why that needs to be replaced, that O2 sensor needs to be replaced, is because that is oxidizing. So that's an oxidation reaction. And so it's kind of using that up, and it's using it up whether you're running tests or not. So it's interesting. It's basically having that chemical reaction either way.
yeah.
And so that's why it has, we say it lasts 12 to 18 months, and we recommend getting it replaced closer to the 12 months so you don't ever have problems.
Yeah.
Yeah.
Now, the CO2 bench is actually really cool. So,
Yeah.
because it doesn't use the same type of technology, it lasts a much longer period of time.
Yeah.
And so, what it uses is called NDIR. So, it's non dispersive infrared. And basically, what it does is it shines infrared light And the way that that reflects off of the carbon dioxide, off of the gas that's in there, it can tell us the concentration of carbon dioxide that's in there. Now, here's one of the interesting things, and this is part of the cool technology that the CardioCoach has, is that water vapor
Hmm.
can affect how that light
Right.
reflects. And so we know that in human breath, there's warm, humid air coming in. And so the machine has to account and correct for that. And so because the machine also measures the amount of humidity that's in that breath, along with temperature and some other sensors,
True.
then it can say, okay, well, we know that this is the characteristics of the breath coming in. And so it corrects for that equation. So it's actually saying this is the actual CO2 versus water vapor
Hmm.
that's being detected here, and then can that becomes much more accurate. And so that's one of the really cool things that we get with indirect calorimetry is they take like real human breath, what's happening at the mouth, and then they're able to um, correct that for to kind of basically create a standardized variable, if you will.
Yep. Yep.
And so you'll see some different terms. So there is like standard temperature and pressure dry. So STPD
Hmm.
versus, um, let's see, body, I think it's BTPS. So body temperature and pressure saturated, right?
Hmm.
So it's basically just saying this is warm, humid air coming from a person versus this is kind of standardized for humidity and everything. Anyway, just you'll
Right.
see those terms sometimes.
Well, really important when you're setting up a study um, to evaluate a metabolic cart that you actually understand that and set up the test accordingly. That if a system's not meant to be run dry, to test it dry isn't an accurate test of how that works,
Yeah.
how it functions.
Absolutely, absolutely. Anyway, so I know I got into your, but it's actually really cool what the system can do and how it uses, um, again, known constants to calculate those percentages, and ultimately combined with flow to give us the amount of VO2 and VCO2 that we're seeing. And so again, like Cameron said, it allows us to draw all sorts of inferences, right? How well are all my systems working together? Because really, like what we're seeing produced in the breath is the orchestration of all those different body systems together to produce a given output, right? As we're increasing workload throughout a VO2 test to maintain that intensity, it's that combination of the heart and the lungs and the nervous system and the muscles and the
So
skeletal
many
system, right?
things.
Like all
Oh
of
yeah.
those things, have to be orchestrated to produce that given work output. And so, um, if we need a higher demand for energy, then we're going to need to elevate our breathing so that we can get more oxygen in. And then at a certain point, we need to get more of that CO2 out so that the cells can keep running. And so that also causes ventilation to increase. And so if things are really efficient, right? If my heart is really efficient at pumping, my lungs are really efficient at extracting energy. I have a lot of blood vessels, right? A great blood vessel highway so that I can get that oxygen to the cell and then I can remove byproducts. If I have a lot of mitochondria and they're really efficient, then that means that for a given workload, right? Whether a given wattage or a given speed and incline, if you're on a treadmill, that I can create that energy more cleanly, if you will, right? I can use more. I can use fats more as a fuel source if all those systems are highly efficient,
Yeah.
and so that will be reflected in the breath data. Am I using more carbohydrates, or am I using more oxygen? And so we can see that in the exchange ratio. We can see that, yeah, in what I'm using there. And so it allows us to draw inferences about how those different systems are working depending on what we see. And because we can, one of the things that I love about the Cardio Coach is you can create custom graphs of whatever you want to look at,
Yeah.
right? So some of the ones that we've talked about before are VO2 per heart rate or per heartbeat. So your VO2 pulse. So that gives us an idea of how the cardiovascular system is working. We can also look at VO2 per breath. And so what's the efficiency of that? We can look at percent fat versus percent carbohydrate, calories per minute of fat,
Mm-hmm.
calories per minute of carbohydrate, all these different things that give us some insight into the system. If you want to learn more about that, go back and check out some of our earlier episodes with Daniel Crumbach. We go through a bunch of those different things that you can look at.
Right.
But that's one of the things I love is you can just look at the data so many different ways with all those different graphs, and it paints a really good picture of what's occurring in that body. And is the major limiter the cardiovascular system? Is the major limiter the respiratory system? Like what are we seeing? What
Or
are happening?
respiratory,
Or
respiratory
respiratory system.
system with, as Daniel would say.
And then, like you mentioned,
Yeah.
that cues us into what questions do I want to ask?
Right.
And this is where you have to be careful, right? Like Cameron said, like you don't want to just say like, oh, your VO2 is really low. Like you better go get this thing tested. It's like, okay, what's the complete picture?
Right.
Did I standardize well enough to draw stable inferences from the data? And so we've talked about that before in previous tests. How do I, run a quality VO2 max test? How do I run a quality RMR test? When we can really dial that quality in, then the inferences that we draw from that data are much more valid. And we're using multiple data points to ask questions and to say like, oh, does this make sense? Or like, what question do I need to ask to make sense of this result that's maybe a little bit strange? So someone that I talked to the other day, we saw that they didn't get um, that heart rate stayed really high um, across the test, but VO2 pulse went down, right? So their VO2 per heart rate wasn't great. Like what was happening at the end of the test, and what had happened is the person had had a hypertensive response
Hmm.
at the end of exercise, and so briefly to explain that, so when we need to create a certain amount of energy, or when we need to maintain a workload of certain intensity, we have to have a given cardiac output, right? So our blood has to be pumping. We have to be extracting oxygen, everything. Anyway, so cardiac output simply is your stroke volume. So how much blood is pumped out with each beat
Mm-hmm.
combined with your heart rate.
Mm-hmm.
If we have a hypertensive response, that can create the afterload. And so the stroke volume goes down, right? Or at least it doesn't increase as much as we'd want to. And
Right.
so what has to increase to maintain the same level of cardiac output? We've got to increase the heart rate. And so heart rate stayed much higher longer than expected, even though like the efficiency changed. That
Yeah.
that
Yeah.
probably
Well,
was not as simple
so
as I could
let's
have put it.
define a couple of terms. So what is VO2, VCO2, those things? So VO2 is the volume of oxygen essentially consumed, or yeah, volume of oxygen consumed while doing work. And so how much oxygen was used in this process. The CO2 was how much carbon dioxide was produced. And so the VO2 pulse being how much oxygen was consumed, how much oxygen was used per each heartbeat. And so it's a proxy for stroke volume, right? And so that idea of as they worked harder because their blood pressure went up so high, now it was your heart's beating against a higher pressure system. And so it's harder to push as much out. It's kind of like putting your thumb on the end of the hose. We're creating some back pressure, which makes it squirt out harder, but the water in the hose is building up a pressure, and that pressure is hard on our heart for one thing, but two, um, it reduces the efficacy of how much oxygen and how much carbon dioxide is being removed and all of those things. So it just gums up the works. And so that VO2 pulse, the amount of oxygen that was able to be consumed, went down per heartbeat. And so that means the heartbeat had to keep going up to try to match the demand of the muscles. And so that's actually a lot of our cardiac events happen with things like that, where we have increased afterload on the heart, meaning it's trying to pump out and it's pumping into a high pressure system already. And so it's puts a lot of strain on the heart. So often that happens too when we just stop exercising without cooling down. The muscles stop calling for oxygen, and so the blood vessels constrict, and we get a lot of afterload. And so that's why a cool down is so important. But those types of things, I think, understanding that what VO2 and VCO2 are fundamentally really does help us understand then what these numbers can mean and how they apply to an actual human.
That was a much better application. Thank you.
I don't know that it was better, but just it's just fascinating to
Yeah.
see how with that VO2 pulse, how that really bears out in a human if you're having a high blood pressure episode, or when we see that kind of not match. Normally you'd see that VO2 pulse kind of go in sync with heart rate and workload and other things. That the harder you work, the more oxygen per breath that you're consuming,
Yeah.
or per heartbeat that you're consuming, or the VO2 breath, or
Yeah.
looking at that with your breath data. Normally, we would see those things go up together. And
Yeah.
when we see that plateau or drop off even, then we know, oh my gosh, there are some things going on here. And so then it helps us ask those questions. Is this a respiratory issue? Was he having trouble breathing enough? Was this a blood pressure issue? It allows you to ask those questions and find out. So when they tested his blood pressure, it was obviously really high. And they're going, oh man, we probably should end the test before this guy keels over on the treadmill. And one of the reasons why testing blood pressure is a good idea.
Yeah. Well, and so like again, this did not diagnose the individual, but it said, like we're seeing this response. What might have caused that? What questions do I need to ask? What other data do I
Right.
need to look at to
Was
make
this
sense
an
of
acute
this?
response? Is this a chronic? Does this happen every time? Or did he get bad sleep? Or did he have a mega dose of caffeine? Did he, like what may have caused this high blood pressure episode?
Yeah. And so just using that data that we can get from just the breath, right? Again, it's
Right.
so cool. But because we're able to combine it with flow and the graphs are just it's taking the data and just slicing it different ways to look at different,
Well, and you can combine it with other measures like blood pressure, with pulse oximetry, we obviously combine it with heart rate,
yeah. Daniel
the breath
uses
data.
spirometry,
Spirometry, we can do the Moxie, um,
muscle oxygen.
muscle oxygen versus the other, where we're doing like the pulse oximetry, we can do muscle oximetry,
Yeah.
and that really is cool.
Yeah.
And so there are other technologies that we can combine that with for even greater depth of knowledge. But just from our breath and combining that with heart rate, oh my gosh, the plethora of information that we can
Yeah.
understand.
And really helping us to design better training plans, but also helping us to really get a thorough history, a thorough understanding of that client and their constraints, right? What limitations does this person have? What are primary limitations, secondary limitations, tertiary limitations, et cetera? And then how can we work with each of those and potentially other medical providers, right? Is this
Yeah.
something that it's like, you know what? I really feel like I should refer out, or hey, let's bring in this specialist
Oh
and
yeah.
we can use this data as an integrated team to really help people improve their health and fitness.
Yeah. I mean, I would use it all the time. I still do, to send people to cardiologists if I felt like that was appropriate, or endocrinologists. We would find findings in their resting and exercise tests where it's like, yeah, let's have you go get some blood work done. That often I would send them back even just to their GP and say, hey, let's get a look at your hormones and see where things are at. And maybe we need a deeper look with an endocrinologist as well. But it just allows you so much data, so many insights to be able to ask the right questions or to dive deeper into certain things to help people not only, train better and train healthier, but also to live healthier. uh, I get asked all the time, well, who's this testing for? Is this like for elite athletes? Honestly, it's for your grandma. It's for you. It's for your spouse. This is for, it's for everyone. I personally believe that everyone should get a VO2 test regularly, um, because we all should be exercising. We all should be, participating in our own health and wellness. And this gives so many insights into how to do that best for your body where you're at right now, so that our exercise efforts really are focused towards what's going to get us the most bang for our buck, keep us healthy, and keep us safe while we're training so that we're not overreaching and pushing too hard.
Yeah, one and this like some people will do this as a one-off test, and that's great. But like we can do this type of testing regularly and then continue to update that exercise plan, that calorie plan for the individual so that they can continue dialing in. And we can see as those body systems are changing. That's what's so cool. It's like here you were at baseline, and now as we've trained this way, we've seen like, oh, you've gotten so much more efficient at using fuel. Oh, you know what? Your VO2 max really went up quite a bit. That impacts your mortality risk. Like,
Yeah. I mean, do you know how many more ATP you're
how you so many more ATP you
the
just
Krebs cycle is just flying in you right
it's
now.
going.
Yeah, yeah. No,
Absolutely.
we don't usually get that nerdy, but I think it's helpful to do that today just to understand where do these numbers come from. And hopefully now kind of this final conversation is what does this all mean for you as a human or for your patients as humans? Like what does that nerdy stuff translate into in terms of how this actually affects and impacts real people?
Absolutely. And I think just understanding that there is good science behind how these things are measured and utilized.
Right. This
This is
isn't snake oil.
snake oil, right? Like, oh, we figured out your mitochondrial age. No, we didn't.
Yeah.
Um, you know, like this is well established in the field of exercise physiology.
Right.
These constants, these relationships, and so I think understanding that it's like no, like what we're measuring actually has real weight. Again, to recap, our body has those three different energy systems, and we use substrate, right? And when we say substrate, that is fats or carbohydrates to create energy. The breakdown of those fats or carbohydrates yields requires a certain amount of oxygen, yields a certain amount of CO2, and then we breathe that out. And so, with what we breathe out, we can again look at what type of calories they are, right? Fat versus carbohydrate, how many calories overall, and then all those other things that we talked about. And so it's just a way. What's happening in the breath is a reflection of what's happening inside our cells as a whole.
Yep.
And then we can use that to again help people design training plans, ask more questions, refer on to other providers as needed. Just really helps us. Like it's just adds this whole huge dimension to taking care of a person's health and fitness that other metrics, as useful as they are, like it's so wonderful to be able to measure someone's A1C, to measure their blood pressure, to look at some of these other things. But just adding in this data gives us an even more complete picture of what's going on in that individual.
Well, so I have used this analogy before. I think early on in the podcast, actually, I said this, but it's fascinating to me how much of our lives, like most of our life, revolves around getting food and eating so that we can stay alive. So we work jobs so that we can earn enough money so that we can put food on the table and stay alive. And so much of our life revolves literally around having enough assets to be able to have food and then eating that food, meal prep and cleanup and all those things, so much revolves around calories, whether we, think about it or not. So much of it revolves around getting calories. And yet, most people never measure in their body how well their body is using those calories. And that's essentially what we're doing. So much of our life revolves around getting calories. And yet we never measure those systems to see, are they working properly? Is what I hope is happening inside my body actually happening? We probably should measure that. It's one of those foundational, like keep us alive things. And yet we rarely measure how well is my body using the fuel that I'm giving it.
Well, and with knowing that, it can help us intervene earlier, right? So a lot of the testing that we do
Yes,
is
so
to
true.
deal with the consequences of it's the sequela of an active disease process.
Right.
And
Right.
so we're measuring your blood pressure, you're hypertensive now, right? In a lot of those cases, we're measuring it regularly if you're getting physical, so we can track some of those changes. But it's like, oh, I'm having these problems, so I'm going to go into the physician, get it tested. Oh, well, man, like look at your A1C. Oh, look at your lipid panel, right? Look at this other blood work. I'm going in because I'm already having these symptoms that are causing problems in my life.
Right.
And then what we measure confirms that. And then we intervene. And obviously, like that is such an important part of medicine, very helpful.
Well,
Like
we save
we
lives.
save
It's
lives,
amazing. Yeah.
crucial, right? I want to be clear on that. Like we're not knocking those other things. They are crucial to keeping people alive, to saving lives, things like that.
It's just too late.
It's too late. And so if we can get in the habit of looking at these things earlier, right? Doing testing early and doing testing often, then we get a picture of that person's, overall metabolic health. How are those different body systems functioning together? And what is this telling us? And how can we intervene now so that we reduce the risk of those sequelae
Right.
later on? So as we've talked about before, cardiorespiratory
Respiratory.
cardiorespiratory fitness, cardiorespiratory fitness is one of the best indicators of all cause mortality, but also disease specific mortality in many
Yeah.
cases. And so we know that for every improvement in fitness category, right, from very poor all the way up to elite, that's a further reduction in risk. And so the more and more and more we improve cardiovascular fitness, the lower and lower and lower our risk becomes. And at certain levels of fitness, it becomes protective
Right.
of those things. And so if we can learn how our body's working and then use that data to design training plans to help people improve their muscular fitness, their cardiovascular fitness, then we can just reduce the risk of so many diseases that aren't like that don't have to happen.
No, well, the lifestyle diseases,
Yeah,
the smoke-a-diabesity diseases, right? The things that we really can prevent. Even some cancers, but not all cancers can we prevent, or not all, kidney dysfunction or other things can we prevent. Sometimes we're just born with genetic anomalies, or
for
things
sure.
just happen, accidents and other stuff. So, but for all of the things that we can prevent, which is actually most of the most common ways that people die, most of the ways that we're dying are actually preventable, especially premature deaths. And so why not take care of those things? Why not lead the healthier lifestyle? Because it's not just about living long either. It's about those quality years, that when we lead that healthier, more active lifestyle and things, we have a better quality of life. So the years that we're around are much better, much more active, much more capable of doing what we want to do. We're less trapped in our own body.
Yeah,
And so that's really what ATP and Krebs cycle and electron transport chain translate into, is by understanding that information and applying that, I can lead a better life and lifestyle that allows me to treat my body more along the lines of how it was designed, so that I can get the most output out of the inputs that I'm giving it.
absolutely. Well, and as you mentioned, there's some things that we can't prevent, right? Every one of us will get sick with something, will get injured at some point, right? Like that's just
Yep.
unavoidable in the course of life. But if we've built a huge capacity, if we've built a huge reserve, when that happens, when I get injured, when I get sick, that doesn't drop me to the level of disability. I have sufficient muscle mass so that I can continue doing the daily activities. I have sufficient cardiovascular fitness that, walking to and from the mailbox doesn't gas me. And so I think that's particularly important, is of building the biggest reserve that we can, so that when life hits us in unexpected ways, we have a much better ability to, you know, absorb that, to move with the punch, you roll with the punches, and come off still able to lead a quality of life, or like if we had a major impact, ability to recover that from that a lot quicker. So we know that in like orthopedic cases, when we do prehab,
Mhm.
the recovery process after the surgery is much better, right?
Right.
We've built that bigger reserve. And so the body can just do what it was designed to do much better, much more efficiently. When we have that really good blood vessel highway, like all the cells that need to get traffic to the area to repair tissue can get there, and those byproducts can be removed and expelled. And so it's just like I know that this was about the breath data, but as always, it turns into the importance of exercise and how exercise really is a poly pill for targeting every body system and making improvements in our overall health.
Yep. Yeah. Well, and the breath data just shows how we're doing with that.
Absolutely.
That's the idea, is we can see how efficiently our body is taking the food energy we give it and turning that into the fuel that we need to be able to do the things that we want to do. And it really is about that life freedom, being able to live life on your terms versus it being dictated to you by your body saying, I can't do that. I want to be in a position where I can make the decisions of what I do and don't do, and not my body being like, sorry, no,
Not today.
not today. I mean, obviously, dunking a basketball is going to be a little more challenging for me, but I could have gotten there. I don't. I guess I still could probably, but
I believe in you.
yeah. But so there's certain things, gifts of height that I don't have, or things that shape kind of what we do, but for the most part, we're really not limited other than by our own effort. And if we're putting those efforts in the right way because we have the right information behind it, we really are limitless in a lot of ways in what we can achieve. And so I love that. I love that we kind of get to test when we're doing a test where somebody's at and how we can help them achieve what their broader goals are, their life goals are.
Yeah. I want to add in one little thing so that people don't misunderstand, because I think I worry what people might have heard is, so much has to do with effort. And
Mm.
person hears that like, oh, so it's all on me, right? I'm the reason that I can't get fitter.
Right.
So to change our bodies, effort is required, right?
Right.
At some point, we have to make changes. But what this information can do is improve our ability to make those changes and to make them sustainable.
Mm-hmm.
And so one thing that having this data does is it helps to combat a lot of the misinformation that's out
So
there
much. Yeah.
about, exercise, about health, about fitness, about how our bodies work even.
Right. And about exercise intensity, what's the best, air quotes, best way to work out.
Yeah. And it can help us to design plans that don't put people into the same cycle of try and fail and try and fail and try and fail. It can help the person to apply their efforts in a way that makes meaningful progress towards their goal. Like people that have failed with other diet and exercise approaches have put in so much effort,
So
much effort, so much time, so much frustration. And yet that effort hasn't resulted in the changes that they were looking for. But if we can get this data and use that to design exercise plans that are sustainable, that optimize for the adaptations that we're looking to optimize for, then all of a sudden that effort goes in the direction of our goals.
Right. Especially when they're based on that person's body, because not only is it more targeted into what are the goals that we're trying to accomplish, but it's more custom tailored to their metabolism, their heart rate ranges, their body, so that they actually can be successful because they're not spinning their wheels working out too hard or too easy or whatever. It really is dialed in for your body. This is going to be the best way for you to accomplish X.
Absolutely.
Right. And so because we can create that more specific roadmap instead of following all of the different blueprints that we see from everybody, that it's like, well, this is how I got fit. But your genetic profile, your food availability, your, so many other things, your
family history,
you're a 23-year-old, and I'm a 45-year-old or, whatever. Like, those differences person to person, the blueprint approach often doesn't work. Whereas when we can sit down with somebody and do more of a roadmap approach of here's your life and lifestyle, and we're going to create your own custom roadmap to navigate your lifestyle and hills and valleys and rivers to cross and all the things that come with life. When we create more of a roadmap, it works so much better.
Absolutely. Oh, love it. Way to tie that all together.
Yep.
Hopefully we gave you some information in a simple enough fashion that you're able to confidently discuss this with clients. Or if you're getting the test, you understand a little bit more about how the machine works and how this data is valid and reliable, and how we can use that to make inferences for health and fitness and lifestyle. As always, thank you so much for joining us. If you want more content like this, remember to like, follow, and subscribe, and we'll catch you next time. Ready to take your metabolic testing to the next level? Visit core.com to learn more about purchasing our metabolic test equipment.